Now I will talk about one of the pilots that is based on Phoenix HPC. So I think some of you may have seen this floating wind turbine pilot, but maybe it's a little bit mysterious. What is it? So here I will show some pictures and give a background what this actually is. And this is, so here I put the people who are working on, connected to this in the MSO4SC project, and there is Daniel Castagnon and Margarida Moragues and Laura Saavedra at Beckham have done some of these results as well. So the motivation. Sorry, Sultan, how long do I have? Is it? Yes, 20 minutes, okay. So the motivation, so why are we looking at this type of problem? So this project started in the Basque country. It's a strong industrial background or framework in the wind power sector. So for example, Iberdrola and Gamesa are huge companies in this sector based in the Basque country. And you could say it's a pioneer internationally, international leader in construction of high technology vessels. So the Basque country is in the Bay of Biscay, a history of constructing marine type of structures and devices. We established then a collaboration between the Marine Energy Unit at Tecnalia. So Tecnalia is a large technological center in the Basque country with about 1,000 employees. And the Marine Energy Unit is led by José Luis Villate. He's actually the chairman of the International Energy Association, the Ocean Energy Systems. So this is a high-profile group. I think with, and I will show a short presentation of what they're doing. So it's a collaboration between the Marine Energy Unit at Tecnalia and the BECAM, the Basque Center for Applied Mathematics, which I'm affiliated with, where I have a part-time position, and KTH. And supported by Euskampus. This is a Basque network for collaboration. And now we have won together a project called ISERMAR from the Basque government. So we now have a formal collaboration. So the research question is, how can we computationally predict aero and hydrodynamic forces on a floating wind turbine? It looks like this. So the idea is that wind energy is kind of a mature field. But one large obstacle is typically that it interferes with population centers. So people complain about visibility interference with wind turbines and also noise. So you would like to move wind turbines away from population centers, from populated areas. And one good potential is far out in the deep ocean where there is no people. and also the winds are higher there. But then there is a challenge to build floating structures then to anchor these wind turbines on. So that is the challenge. How can we predict the dynamics of this before they're constructed? So these are massive, maybe 50 meters long. It's not feasible to do experiments at full scale. So again, I just repeat what I said before. We have a multi-phase model that covers this type of phenomena, so aerodynamics, braking waves, and with a simple extension, fluid structure interaction. And as I introduced before, we have the method that we call direct FEM, General Galerkin also, and we realize the methodology in Phoenix HPC. So this is how we implement methodology and carry out simulations. So now we do step by step. So first we look at only the platform, and we start with only the submerged part. So we start with a one-phase model to only look at the water flow past the platform. So then we we apply the method as I explained, and with adaptivity. So on a coarse mesh, it looks like this. We see separation on the back of these cylinder parts of the platform. With an adapted mesh, we resolve structures. So we have these sort of streamwise vertical structures which correspond to the drag on this. So now we can actually resolve the forces on the platform. And this is at full scale. So the Reynolds number is very high, which fits with our zero friction model of the boundary layer. And here is a movie showing the surface velocity field. So as you can see, it's a time-resolved turbulent solution. And this is this adjoint solution that we use for the adaptivity to get the sensitivity. So where this is high, you take the inner product of this with the residual. So this basically says where this is high, the residual is the error is sensitive to the residual. And we did some a basic study of mesh convergence. So we can see that it's difficult to do experiments on this, but the experimental values that we can find in the literature lie between these 0.5, 0.8, and we see that the last adaptive iterations lie in that region. So I think it's a reasonable preliminary result. And based on this this work, we participated in the Bilbao Marine Energy Week together with Technalia. And they thought this was a very interesting direction. So we won the Best Poster Award. And in the Basque Country, if you win something, you get a hat. So this is Vincenzo at Technalia, the main contact person. So now I can show also the... so here is the Marine Energy Group at Technalia. It's just a very short presentation of what they do. So Technalia Research and Innovation, as I said, it's a huge center. They do a lot of things, health, transport, ICT, and so on. So we work with the Energy Environment Division. And out of the 1,000 people, we work with this team, the Marine Energy Unit. And here is José Luis Viate, the head. And I can't seem to find Vincenzo, but you already saw him here, I think. So they look at different types of devices. So offshore wind and wave energy. And typically, I don't think it's not part here, but also spin-off companies. So Nautilus is a company that is actually designing such floating turbines. And the challenges are then it's very harsh environment. So it's the ocean, you have salt water, and you have sort of extreme waves and so on. So survivability is a key problem. Let's see, I have two open here. This one. So this was one phase, kind of a simplified, similar to what we did before for aircraft and so on. But we want to have waves. So now we allow the density to vary. So it's still an incompressible model, but with a variable density. So we can say that we give the density of water as an initial condition in one part of the domain and the density of air in another. And then we simply solve this this equation. So where you have then an evolution equation for the density, and the density appears in the momentum equation. But it's still incompressible, so divergence free velocity. What we can apply this direct FEM methodology directly. So then it's a completely automatic, nothing specific to multiphase. but there are some issues with preservation of the sharp interface that I will show. So what we have done is to do one explicit modeling for multiphase, is that we add a phase separation term. So these other terms are all terms from the finite element method, and this is stabilization. But then we add this term, which we call phase separation, where you have these two densities of air and water appearing. So this has a bistable form. So what you can see, for example, this term is zero if the density takes on either air or water, but it's non-zero if you get intermediate values. And these intermediate values are just a numerical artifact. We're supposed to have immiscible flow. They're not supposed to be able to mix. So the diffusion we have is numerical. So this term is kind of like an anti-mixing or a phase separation term, which is supposed to remove this numerical artifact of mixing. So we implement this, and as a validation, we look at a standard benchmark called the marine benchmark. So it's by the marine lab in Holland. So I think the motivation for this comes from a container on a ship. Then you have a wave hitting, and you have pressure sensors in this container. So in the lab it looks like this. You have kind of like a dam break, so an initial body of water, and you remove a wall, and you generate a wave that travels back and forth hitting this container. So then we should predict then what is the pressure on this container in some sensors. So as you can see in our simulation, we can reproduce the basic phenomenon of this crashing wave. And here you can see to the right. Here we just apply the direct FEM method directly without anything specific to multiphase. But as you can see, we get the kind of a mixing. So we get these intermediate values of the density that has a kind of diffusive effect. Here to the left, we introduce this phase separation term. And as you can see, it kind of forces the density to take on either of these two values, still in a mass conservative way. So we preserve the mass. But so it acts like a sharpening of the interface. and it allows us to get a more accurate solution for long times. So we can look at this one more time. So you can see there is a second wave. So the wave travels back and hits. And in the phase separation case, we capture the second wave for long times, whereas in the standard sort of method, this second wave is kind of diffused. We can look at this in the plot as well. So in the experiment is the green curve, and the simulation with separation is the red, without separation, the blue. And as you can see, the blue, first of all, the blue curve, even though it was not visible in the movies, it completely misses the first pressure peak, which is the important. So this is where the first wave hits the container. And this is the pressure you're interested in to see if the if the box survives the wave. So you get the wrong pressure and also a kind of diffused solution. So here it's just a flat solution, whereas in the red curve with the separation term, we get a reasonable prediction of the pressure peak and also the second wave. So this is comparable to the literature. It is not, there are results which are a little bit better, so we are kind of, but I think it's an interesting, what we have here is the part of an adaptive methodology and so on. So I think we have a more general methodology with this. Now we go to, I haven't described the model here. So what we're interested in is the platform floating. So we also need a rigid body model So this is a standard, just a rigid body with a moving mesh with an ALE method that we have implemented. And then we participate in another benchmark by the IEA-OES, the International Organization for Ocean Energy Systems. We have a project with them to validate software for wave energy and this type of problems. So here is the problem. It's a floating sphere, heaving only in the y direction, and the goal is to predict then the dynamics of this sphere. So here is our simulation, where we now have a moving domain. And here is some preliminary results. So there is still no experiment to compare to, but there's a lot of participants here. It's almost impossible to see. But in our preliminary results then, we can, which is the purple line here, we can match sort of the first peak here. And then it seems that we have less dissipation than the rest. So we have done this on one mesh. But I think it's a good preliminary result. So now we actually have a method to do heaving geometries. So in the current and future work, we do not only a sphere. So now we realize the full platform, floating platform. We do fluid structure, we want to do fluid structure interaction. So we actually want to see the forces and the deformation of the platform due to these extreme waves. And we want to add then this general adaptivity. So for fluid structure interaction, we have already published partial results for this. And as part of the MSO for SC project, we have started running these cases in the system, in the prototype system as it exists. And it seems to be working reasonably well. So I would say this is promising. And I would like to acknowledge then also funding from the Basque government, the Spanish government, the EU, and these are supercomputing, the PRAISE, and the Swedish correspondent to PRAISE. So thank you very much.